model. Okay, so tell me what are the postulates we have discussed in Bohr's atomic model in the last class. Want a quick revision of those? Like atom is considered to be spherical in shape, okay, in which the nucleus is concentrated at the center. Okay, then next, so electrons revolve around this nucleus in circular paths called orbits. So these orbits have fixed energies and fixed radius. Okay, and next, only those atomic orbits are allowed in which whose angular momentum is quantized. So quantized means angular momentum should be equals to L. Angular momentum L is equals to NH by 2 pi. Okay, now again what is the angular momentum we got? MVR sin theta. Okay, sin 91, so MVR equals to NH by 2 pi. So this is the equation 1 we have considered in the last class. So from this again we have derived what is the value of radius we got? Formula for radius we got as 0.529 n square by z. Okay, so derivation everything is discussed in the last class itself. Okay, and then next, radius is over. Velocity of an electron in the nth orbit 2.18 into 10 power 6 z by n. So here for radius angstrom units I am saying, for velocity I am saying meter per second units. Okay, these are the things we discussed and numericals related to this discussion we done in the last class. Right now, yeah. So radius over and velocity also discussed, few questions also given. Okay, so one last question just to revise that. Okay, so now tell me what is the radius of, see, so radius of okay, so radius of second orbit of helium plus ion is x. Then radius of second orbit of Be plus 3 ion is dash times x, dash times x. Okay, what is that value in this dash I can fill? So tell me. So how can you do this? See, radius of second Bohr orbit of helium plus. So what is the radius formula I just now told you? 0.529 I told you. Okay, so this value is considered equals to 0.529 by into n square by z. So n square is how much? 2. Second orbit now. So 2 square. 4 I can take. Z, what is atomic number for helium? 2. Okay, by, and here radius of what I am asking? Second Bohr orbit of Be plus 3 ion I am asking right now. So how much here? Again 0.529 into n square. So second 4 by 4. Atomic number for beryllium is 4. Okay, so this I can remove. Okay, and this will be 2 times, this will be 1 time. So what you got? So radius of helium plus. So here is how much I told you, radius of helium, how much I told you here? This one. X. This is x I told you right now. So x equals to 2 and here we have R2 of plus 3. So what I can write? R2 of Be plus 3 equals to 2 into x. So what is our answer here? 1 by 2. Is that clear or not? Clear now? So like this they will ask, they will be giving x or a naught for some value, for helium or some other species they will ask for another relating to it. Okay, similarly velocity also they can relate like this. Okay, next after this All the discussion of radius and velocity done in the last class. This is just a simple question based on this. Okay, next we need to discuss about energy. Okay, energy of electron present in nth orbit of hydrogen atom. Okay, so for that we can get the value as En, energy of electron in the nth orbit, is equals to minus 13.6 Z square by N square electron volt per atom. Okay, this is one formula. Like this, by changing the units, so we can write in joule per atom as minus 2.18 into 10 power minus 18 Z square by N square. So all these formulas are important here. So now what I am asking is, what is the energy of electron revolving in the first Bohr orbit of hydrogen? Tell me. Energy of electron revolving in the first n equals to 1 of what? Hydrogen atom. It is equals to minus 13.6 into Z square. Hydrogen atom atomic number 1 and n principal quantum number, how much I am saying, n value is 1. Okay, so so that is minus 13.6 electron volt per atom. Similarly, if I ask for second energy, like electron in the second Bohr orbit of hydrogen atom, so what you will get? So same value, minus 13.6 electron volt. See, Z value is how much, atomic number is how much for hydrogen? 1. So 1 here, and n value is how much? How much I am saying? N equals to, here in this case 2, 2 square 4, so 4 here. Okay, electron volt per atom. Okay, like this if I ask you, so what is this? I can say 3.4 minus 3.4 electron volt will get. Like this if you keep on doing, you will get some successive values. We will see that. Now just write one question. Energy of electron in the second Bohr orbit of helium ion. Yeah, tell me.
Minus 13.6 into
energy of electron revolving in the second Bohr orbit of helium ion. Minus Z square by N square na. So second 2 square, so that will be 13.6. First Bohr orbit if I ask,
13.6 into 2.
13.6
into 4.
13.6 into 4. Only Z is changing here. Okay. So now what I can say, E1 of helium ion I am asking na. So what you are writing? Minus 13.6 Z square by N square. So N is how much I am saying? 1. So minus 13.6 here 4. Okay. So simply I can write Z square here. Okay. That is 4 you are saying. 4 by 1. Okay. So E1 of helium is equals to, I can write E1 of helium equals to 4 times of E1 of hydrogen atom. Can I write like that? Yeah. Why? Because what is the E1 of hydrogen atom you got? 13.6. So instead of writing minus 13.6, can I write like this? Yeah. So E1 of helium plus is equals to 4 times of, like this. So this is nothing but, if I ask directly without solving anything, I am asking E1 of lithium plus 2 will be how many times of hydrogen? Simple. What is the atomic number here? 2 square. So here lithium atomic number is 3. So 3 square, 9 times of E1 of hydrogen. That's it. If I ask for beryllium, 16 times of hydrogen atom, like that. Okay. Yeah, clear now this discussion? Yeah. Next thing is if you keep on calculating energies, what is the ground state energy for hydrogen atom we got? Minus 13.6. First excited state I can say, otherwise second level I can say. That will be how much we got? 3.4. Similarly, if you solve it for minus 13.6 into Z square Z is 1, n square is 3, I am saying 9. So how much it will be? Electron volt per atom. So you will going to get this value 1.51 minus 1.51. Like that, if you keep on increasing the n value, what happens? Energy is becoming less negative or tending towards
More positive.
0, tending towards 0. So what is the energy of electron which is staying in the infinite level? Infinite level means what? Like here, what I should take here, instead of taking n square, infinite square means something by infinite will be 0. So infinite energy is how much? 0. So as n value increases, energy also increases. So what is the maximum energy you are seeing? 0. It means if you take an electron which is at an infinite distance from the nucleus, it has energy of 0. If it is in the first level of the hydrogen atom, it has energy minus 13.6. Okay. So now if you observe as n value increases, what happens to the energies? Energy is increasing. Okay. But what about energy difference between the energy levels? Difference I am saying. See, first difference is how much? 10.2. Second difference is how much? 1. So I can say as n value increases, energy also increases, but energy gap between them decreases. So this is 13.2, 1.89, like that. So energy gaps are decreasing. This is a statement based question you can expect. As n value increases, what happens to energy levels? Energy levels also increases, but energy gap decreases. Okay. So maximum energy gap will be seen in the
N is equal to
1 to 2. Okay. So it means in order to excite an electron which is staying in the first state to from ground state to first excited state, how much energy required? 10.2 electron volt of energy should be supplied. Minimum of this much amount of energy should be supplied to this to make its excitation. If you supply lesser than this, electron won't excite. Okay, right. Okay. It will excite, but it will goes to which level? Only first level. Okay. If you supply this addition of this one plus this one, then it goes to second level. Second level here. Second excited state or n equals to c. See, I am saying first excited state, that is also same as second state. First excited state n value is how much?
N value is
2. Ground state means n equals to 1. First excited state means n equals to 2. Okay. Yeah. Next one is, see, now what is the thing you are going to expect here? See, now you can have electron. For example, electron is at here, the fifth level. So electron can falls into the directly into the ground state. Okay. Or electron can falls into the second state, or it may falls into the third state, or it may falls into the fourth state. Like this, different possibilities are there. Okay. So during that process, what happens when electron falling from higher energy to lower energy? Emission of energy takes place. Okay. We can say that is emitted energy. Okay. So during this, how many spectral lines are possible, they will ask. It means when an electron is falling from fifth energy state to first level, how many emission lines are possible? That is what we are calling it as spectral lines. Okay. Not 4, more than 4 it is possible. I will show you. Okay. So look at here. When we have like different energy levels, we discussed it now 1, 2, 3, 4, like that. So it can comes from any higher energy state to first state. It means ground state. We should call those lines as Lyman series lines. From any higher energy state to first excited state or n equals to 2 value means you should call them as Balmer series lines. Okay. Any higher energy state to third state, Paschen series lines. Any higher energy state to fourth, bracket, and fifth, fund to sixth, it means Hamfare. Okay. So now these Lyman series lines appears when you wanted to check whether this line is appeared or not. So it will be observed in UV region. Where it is? UV region. And Balmer series lines appears in visible. Okay. And Paschen, bracket, fund, all this appears in IR. Easy to remember. First one, second, visible. All the other are IR. Okay. This is an important bit. Okay, so now look at here. So what I told you, Lyman series means any higher energy state to first that appears in
Ultra
UV region, and any higher energy state to second visible, any higher energy state to third IR. So remaining also all are IR only. Okay, like near IR, mid IR, far IR you can say. Okay, in the range of infrared. Okay, next thing is, now the question will be like this. So what is the energy formula we have discussed? Minus 13.6 Z square by N square. So now what is the energy difference if I ask?
E2 minus E1.
Like you are saying na, E2 minus E1, E final minus E initial you are saying na. So now where you will see maximum energy difference in the Lyman series? Infinity to
1.
ground state, right now.
Which is 13.6.
That is maximum of 13.6 electron volt we will be seeing. Okay, and see what about energy and wavelength relation? See, E equals to h c by lambda we are writing now. So h c by lambda or h nu we are writing. So or h c by lambda. So here what is my explanation here I wanted to give is, see, maximum energy difference means maximum frequency and minimum wavelength. So now the question in the exam will be comes like this. Identify the transition of electron with maximum wavelength in Lyman series.
Low energy.
Lyman series maximum wavelength. In Lyman series I am asking maximum wavelength transition and minimum.
Alpha.
So tell me from where to where you will say for this. So maximum lambda means minimum energy. Like this, maximum lambda, minimum energy. So minimum energy is observed in which case? Energy difference should be minimum.
10.2
2 to 1.
2 to 1 will be the minimum for Lyman. So I can say N1 equals to 1, N2 will be 2. So 2 to 1 transition will be having minimum energy, maximum lambda. And for minimum lambda, that is max energy. Tell me.
Infinite to 1.
So N2 should be infinite
N1 is equal to 1.
1, like this. Is that clear? Yeah. Next, tell me similarly for Balmer series.
Balmer series for maximum or minimum.
Tell me for maximum lambda.
3 to 2.
N2
Maximum lambda.
N3 to
So minimum energy difference you check. Minimum energy difference means,
3 to 2.
3 to 2.
see, we are talking about Balmer. So 2. So 3 to 2 is minimum energy difference. So maximum lambda. So 2 to 3 to 2, like this. And for this one, minimum lambda means infinite to 2. Okay, this is a transition you can remember. And you know, some other lines are also known to be discussed here. Yeah, so look at here. Yeah, see here, what is the first line in the Lyman series? First line in the Lyman series is, what is the first line, n values for first line? So n2 should be 2 and n1 should be 1. So this is the first line of Lyman series, or also called as H alpha line of Lyman series. And what is the second line of Lyman series?
3 to 2.
3 to 1.
This one is fixed from here. So just see what is the difference between 1 to 2 means 1. So first line. Second line I am asking now, 2 minus 3,
2.
like 3 minus 1, 2. So this will be the second line. Similarly, tell me what is the fourth line in Lyman series?
5 to 1.
5 to 1. Is that clear? Now, what is the infinite line? It means infinity to 1. Okay. Similar to this, tell me first line in Balmer series.
First one is 3 to 1. 3 to
Balmer series. So Balmer series is 2. First line means 3 to 2. And second line means
4 to
4 to
2.
2. This is the second line in the Balmer series. And in the Paschen series, you tell me second line.
Second line n is equal to 3. 6 to
3. If I am writing 4, it will be first line. If I write 5, this will be the second line. Okay. Now they will ask like what is the wavelength or energy difference for the third line of Paschen series or second line of Paschen series or Balmer series. Okay. Based on this, you can able to answer that. Okay. So now so energy transition. See what we have, E final minus E initial we discussed, like energy difference means. So what you are going to get, if I want to talk in terms of electron volts, you just simply take minus like 13.6 energy difference na E2 minus E1 or E final minus E initial means you take N1 square minus N2 square like this. And this is for hydrogen atom, and if it is other than hydrogen atom, Z square. Just take here, so here I will insert 13.6 Z square to 1 by N1 square minus 1 by N2 square. Always N2 should be greater than N1. Okay. So now just tell me what is the delta E will get for N2 equals to 2 and N1 equals to 1 means? Yeah, so that will be 13.6 hydrogen atom only I am saying. Okay, so it will be 1 minus 1 by 2 square, so 4 here. So 13.6 into
10.2.
So here
3.
see
4
4 minus 1 3 by 4 like this. So the next
4 3.2.
yeah, like that you can just simplify. This will be how many times?
3.2.
3.2 into
3.4 sir.
3.4. Okay, so 12 10.2. So that is what we have seen in the like here also. This gap here I have shown a 10.2. Same value will be in this case. Now if I ask for lambda, so wavelength, you just remember this Rydberg's equation, 1 by lambda equals to, you can take this as RH Z square 1 by N1 square minus 1 by N2 square. Okay, where what is mean by RH here? Rydberg's constant. How much it is? 1.1 into 10 power 5 centimeter inverse you can take, or 1.1 into 10 power 7 meter inverse you can take. Okay, Z means its atomic number, whatever the numbers they are saying. For first line of Balmer series, if they ask how do you find this lambda, no? First line of Balmer series means what are the N1 and N2? Just now we discussed Balmer series.
N1 is 2.
Balmer N1 is 2 and N2 will be 3. That's it. So substitute these values here. For if they say hydrogen atom, take Z is 1. Okay, and yeah, that's it. So just take it as 1 by lambda equals to RH. If I am saying hydrogen atom 1 into, so this will be 1 by
36.
So this is Balmer series now. So Balmer means here 1 square 2 square 4 here
4
and here 9 here for Balmer series I am saying. Okay, so 1 by lambda, so RH 9 minus 4 5 by 36. Okay, then lambda will be 36 by 5 into 1 by RH. Okay, like this. So there are some questions like giving what is the lambda value for this particular transition. Okay, so similarly if they ask for Paschen, second line of Paschen,
N1 equals to 3, N2 equals to
5. That's it. Difference should be, if I say second line, difference should be 2. If I say third line, difference should be 3, like that. If I say fourth line, difference should be 4. That's it. Whatever may be the series. Okay, that's it. Okay, and is this clear up to here? And now we'll discuss two other formulas are also there here. So remember, so time period of revolution, it means how much time is taken for like revolution, I mean for rotation of like revolving around the nucleus. We have electron will be revolving now. So for this, how much time is taken, okay, per revolution, okay. So I am saying it as T, time period. You just use this formula 1.5 into 10 power minus 16 n cube by z square, okay, very important formula it is also. And next, frequency of revolution. See, time will be in seconds we will get,
Per second.
okay, per second I am saying, okay. So seconds, okay. Now this frequency is like, what is the unit of frequency? We have second inverse or hertz, right now. So it means this is second inverse means frequency is nothing but 1 by time period. So inverse of this will be the frequency, okay. So if you do this inverse of this, you are going to get 6.6 into 10 power 15, see, n cube in the numerator, n cube in the denominator, z square in the denominator, z square in the numerator, just reciprocal of this you can say, okay. Remember these two formulas, okay. Next, now just write one question. Energy of electron revolving in the second orbit of helium ion is x, then
In the second orbit of
helium ion is x, then energy of electron revolving in the second orbit of beryllium plus 3 ion. Okay, what is the question I am given? So energy of electron in the which orbital?
n equals to 2
second orbit of
of helium.
beryllium plus 3 I asked.
Yes, you gave helium x.
So helium E2 of helium plus is how much I given x, that is nothing but minus 13.6 z square by n square. So
we can remove it as
z is how much for helium? 2 square, and n is also 2, so 2 square. So I can say this value, wherever I have this value, that is equals to x now, okay. So here also I can write minus 13.6 into z square by n square. So minus 13.6 is nothing but x into beryllium 2.
16.
So here it is 2 square 4 and here 16. So 4x.
Sir, unless we can cancel 2 n's in the both equation and just
Like that also you can take.
to z square.
Like that also you can take. Okay. Now one more term we need to study here is ionization energy. So what is this ionization energy? For example, here we have nucleus. Okay, this is a nucleus. So if this is the first orbit, this is the first orbit I am saying, this is the infinite level orbit. So the energy required to move the electron from this first level to infinite distance. So how much energy required? this much energy required, that gap, whatever the gap we have. So now ionization energy should be written as delta E. The delta E is nothing but E infinite minus E1. Yes or no? Can I take it like that? Yeah. So ionization energy equals to, infinite means what?
Zero.
What is the formula? Minus 13.6 z square by n square. What is the n value here?
Sorry.
Infinite means n value is infinity. So something by infinity will be 0. So E infinite will be 0 minus of E1. So that is nothing but minus of minus 13.6 z square by n square. So ionization energy will be in terms of positive. Okay, same value as total energy, but that will be in positive value. Okay, 13.6 z square by n square. Okay, so now tell me ionization energy exothermic or endothermic? What is the sign you are seeing here? Positive, no? So it means heat is absorbed. The energy required to move electron from first state to the infinite level. Okay, so this is endothermic process. Okay. So now if I ask the ionization energy, write the question. Ionization energy of electron present in the first Bohr orbit of beryllium plus 3. Beryllium plus 3.
16 into 13.6.
Hmm?
16 into 13.6.
So what I am saying, IE of
Plus
which one I asked? Beryllium, na? 4 square and which orbit? First. Okay. So you can say 13.6 into like 16. That is nothing but I can make a simple formula now. Ionization energy equals to 13.6. Whenever I say first ground state, generally you can take 13.6 into z square. For if I ask for helium, just 13.6 into 2 square. Helium atomic number? 4. Okay, like that. Okay, so now just now I have given you something like different series of lines like this. I have told you this is 1, this is 2, this is 3 and this is 4 and 5 I have given you. Okay, now I have an electron in the 4th level. Okay, now how many number of spectral lines possible when it is falling from 4th level? Total number of spectral lines possible when electron is falling from 4th level.
4 to n.
See, it can fall from directly from 4 to 1, okay, or it might go to 4 to 3, from 3 to directly to 1, or from 3 to 2 it can go, and 2 to 1 it can come, right now. So again any other possibility we have again. So 4 to 2 directly it can come, 4 to 3 over, no? 4 to 3, 2 it directly come, and 2 to 1 already written. Any other possibility? 4 to 1 over, 4 to 3 over, 4 to 2 over. Next 3 to 2 over, 3 to 1 over. Okay, next 2 to 1 over. So these are the number of spectral lines possible. How many? 6 we got. Okay, all the time writing like this and counting it is very difficult, right now. So we can have a simple formula here. Okay, so whenever I say ground state, okay, whenever I say ground state, you just use n2 minus n, like n2 minus n1 into n2 minus n1 plus 1 by 2. For any number of states you can use, whether it is ground state, first state, second state. This is number of spectral lines possible. Okay, just place this n2 and n1. What is our n2 in the question? 4. N1 ground state I am saying now 1. So place these values here. Tell me.
3.
So 4 minus 1, 3. Again 4 minus 1 plus 1. So 4 by 2.
12 by
Okay, so
this is the
6 lines we got. Here also we got 6 lines now. How many lines are there? Yeah, that will be our answer. Okay, just write one more question now.
Sir,
Tell me.
2 is 4, right?
Okay,
N1 is 1.
okay.
1 plus 1 is 2. So
1 minus
4 minus 2 is 2. 2 to cancel the 3 no answer.
Once again,
Equation 3 is the answer.
4 minus 1. How much?
3.
Board mass rule, sir. First addition, then subtraction.
Okay, so what you want? 4 minus 1 plus 1. Okay, 4 only, no?
4 by 2.
Why you are getting different answer? Is that clear or not? Okay, so do one more question I will give you. Number of spectral lines. Number of spectral lines possible when number of spectral lines possible when electron falls from fifth level to ground state. 5 to 1. Yeah.
5 minus 1 equal to 4 into 4 plus 1 5 5 4
10.
5 20.
How many?
10. 10.
10 spectral lines. Okay, so 10 spectral lines. Now they will ask, out of these 10 spectral lines or out of these 6 spectral lines, how many are lying in Balmer series? Here we got 6 lines for n equals to 4 to 2 now. How many lines falls in Balmer series?
Balmer is n equals to 2.
How many lines falling in Balmer series?
N is equals to 2. One second question, sir.
How many out of these 6 lines, how many falls in Balmer series?
3, remove 3, only 3.
Balmer series means any level to
2.
second level. So how many lines are there in second level?
2.
See this one and this one. How many lines are in Balmer series? 2. How many lines in Lyman series? 3. See 1, 2, 3. And Paston series? 1. So I will tell you one simple trick here. So what is the highest, what is the N2 value I given?
4.
So N2 I given now. If I ask Lyman series, what is the Lyman series bottom line? 1. N1 equals to 1. So N2 minus 1 you do. So N2 is 4 minus 1. You will get 3 lines in the Lyman series. So 1, 2, 3. Okay. So formula is N2 minus, like N1 means that 1 represent that particular spectral line. For example, like Lyman series, Balmer series I am asking. Tell me Balmer you told 2. So 2 minus 4 minus 2 here you got 2 lines. Okay. So now tell me number of spectral lines. Now what is the question you have made previously? 5 to 1 ground state. Now in that out of the 10 lines, how many are in visible region?
Visible region and 10 only, sir.
How many lines are in visible region?
9.
Balmer is n equals to 2. So 10, 8. Sir, n1 is
Be conscious.
10.
Out of the 10 lines,
3.
3. So N2 value is how much?
5.
5.
5. Balmer series means
2.
2.
2.
2. 5 minus 2.
3.
3.
Okay, that is from 5 to 3, 4 to 3.
3.
What I am asking? Which region? Balmer series. So 5 to 2, 4 to 2, 3 to 2. These are the 3 lines possible. Is that clear or not? Yeah. So if they ask for what is the wavelength means, you should take N1, N2, N1 these values and do the problem. Like what is the formula you should use?
RH 1 by n1
RH Z square.
z square
1 by
n1
n1
square minus 1
by
by
n2 whole square.
n2
Square
where n2
should be greater
greater
than
than
N1. Okay, that's it. Okay, and Abdul Rahman is in online today.
Hi.
ఇంపేదరా వాయిస్
ఎందుకు
మైక్ ఆఫ్ చేసుకో
Okay, so okay, so what we discussed today, tell me.
Today.
Hmm.
Observe the spectral line.
Number of spectral lines and energy difference between the different energy levels. Next, frequency. Next, time period. Finding wavelength using Rydberg's equation. Okay, and the spectral lines possible and in which region they fall. And tell me what are the limitations for Bohr model.
Hydrogen spectrum.
It does not explain
other spectra except hydrogen.
And it is applicable only for single electron species. It means single electron means like that, like now you have written that many number of questions.
Li2 plus
All of them are something like hydrogen atom or helium ion you have written, or
Li2 plus
Li plus 2 you have written, or
plus 3.
Be plus 3, like this you have written. So all of them have what? The similarity is only one electron. Single electron species only it is applicable. And next thing is, it does not explain the splitting of spectral lines. Now you are calculating number of spectral lines now. So these spectral lines further splits when I place external magnetic field or external electric field. The like what I can say now, it does not explain the splitting of spectral lines in presence of magnetic field. That is considered as Zeeman effect.
Stark and Zeeman.
And one more is Stark effect. It means in electric field. Okay, it was not explained this. Okay, these are the main drawbacks you can remember. Okay, yes. So this is about the thing. And if you want, ask me. Okay, nothing to ask. Yeah. Yaqub Ali. So just Yaqub Ali in the chat box. Just contact to the number which is given in the description. Okay, so you will get further details.
Can you post daily your notes in Telegram?
Yeah, sure.